Assalamualaikum warahmatullahi wabarakatuh. Good morning, everyone. Thank you for joining this session. So, in this session, I would like to cover actually two topics. One is flexibility method, and another one is moment distribution method as preparation for test for 30% test on this Friday. Basically, we will focus on how to analyze structures, how to answer question, and we will look at some of example, and we will hands-on how to calculate, how to analyze reaction in indeterminate beam, frame, and truss. So for today, we will focus on beam and frame analysis first for flexibility method. So for the revision, so in flexibility method, we use flexibility method to analyze indeterminate structure, including beam, truss, cable, truss, frame, and composite structure. And anyway, we can analyze all type of structure, including cable and arch as well. But we focus on the scope for this topic is just to focus on 4 types of structure, including beam, frame, truss, and composite structure. Okay, so there are 2 types will be covered. One is for degree of indeterminacy, which is equivalent to 1, and equivalent to 2. Redundant is equivalent to 2. So we will do example considering both DOI equivalent to 1 as well as equivalent to 2, means redundant, number of redundant in the system. Okay, so the concept is, so always remember that the most important thing is we understand that we use flexibility method whenever the 3 equilibrium equation is not enough to solve the reaction in the system, because there are more than 3 unknown reaction. There are 3 unknown reactions. So we get degree of indeterminacy equivalent to 1 because we get from the formula. So the simple formula to analyze to find the redundant is by using 4 minus 3. So this 4 minus 3 is actually 4 minus 3 is actually 4 is number of unknown reaction in the system, number of unknown reaction in the beam, and 3 is actually representing reaction which can be solved using equilibrium equation. Okay, which can be solved using equilibrium equation. So we get 1. So the 1 value here, this is 1. Value 1 represent redundant, and this redundant need to be solved first. So we have to solve this first. Solve this first. And once after redundant has been determined, then only we can analyze remaining reaction, which is 3 remaining reaction. Okay. So this redundant have to be determined by using what we call as compatibility equation. So it comes from the principle of superposition. And using principle of superposition, we get the equation like this. Actual beam is equal to primary beam plus redundant beam. And primary beam plus redundant beam both actually has the same type of beam. Okay, this is determinate structure. Redundant beam also determinate structure. Actual beam is indeterminate structure. Okay, and normally whenever we analyze structure, we call redundant structure or redundant beam as redundant applied. Redundant applied because the redundant that we remove, we apply back into the beam. Okay, as not as support but as an applied load that is subjected into the system. Okay, into the system. Okay, so I don't want to derive the compatibility equation, okay, this time, because we have discussed that previously. So I want to focus on examples, okay. So let's do one example. And okay, let's review the example that I have actually prepared previously. Okay, okay, this is one example. Okay, this is one example. So this is a beam, okay, with one end at fixed, one end fixed and one end roller. B is roller. B is roller. So we remove BY as redundant. We remove BY as redundant. So once we remove BY, so we straight away get the compatibility equation. Compatibility equation. This is the compatibility equation. We get compatibility equation. Okay, compatibility equation. Delta B naught plus FBB dot BY is equivalent to 0. Means that we will use that equation to calculate BY value. BY value. Okay, so step number 1. What is the first step? Step number 1, we choose redundant. Okay, step number 1, we choose redundant. Okay, step number 1, we choose redundant. And then why we need to choose redundant? Because we need to remove redundant. We need to remove redundant because there is extra reaction due to redundant. So once we remove redundant, the structure become determinate and stable. The structure become determinate and stable. So we determine redundant because we want to remove redundant. And after that, after remove redundant, we have to draw the primary structure. Primary structure is actually after removing redundant, if BY is the redundant, so we get cantilever beam as the primary beam. So redundant beam also cantilever beam. Redundant beam also cantilever beam. So there are two systems to be analyzed. The first one is called as primary beam. The first one is called as primary beam. Primary beam, this one, primary beam and redundant beam. So there are two determinate system. One redundant, we have two determinate system. Two redundant, we have three determinate system to be analyzed. One redundant, we have two determinate system, including primary system. Primary system is a beam, is a determinate beam subjected to all external loading. Redundant beam is redundant BY applied. It is a beam, determinate beam subjected to a unit value of redundant. So in the redundant beam, we just put a unit value into the system and we calculate the reaction due to a unit value. We put BY outside. Okay, so after that, what we need to do? So once we have primary beam and redundant beam, we have to calculate reaction. We have to calculate reaction for both diagram. Reaction. So this is just a simple beam. So we get AY for primary beam equal to 100. And then we get moment equal to 400 counterclockwise. So we calculate also the reaction due to a unit value. We get -1. And then we get moment 8. Okay, moment at A is equivalent to 8. So due to that, we write the moment equation. And we have two cutting section. One is for section AC and another one is for section BC. Okay, so the first cutting section is AC, origin at A, and limit is from 0 to 4. So be careful with the sign convention. Whenever origin is come from left, the moment is counterclockwise. When origin is come from left side. And when origin come from right side, this is right side. When origin is located at B for cutting section number 2, okay, the moment is clockwise because origin come from right side. Okay, so we write the moment equation. There are 4 moment equation. So this moment equation we substitute into the displacement formula. So inside compatibility equation, it is actually displacement at the redundant position in all system. Means the position of redundant is located at B, position redundant is located at B. So we have to determine the delta, the deflection at position B for primary beam, and we need to determine also the deflection at position B for redundant beam due to a unit value of redundant. So we get delta B naught and FBB. We can also use label delta 11 and F11 because of this. Okay, so either one can be used, but please do it consistently. Okay, so using formula, we integrate to calculate, delta B naught, So we use notation that we use. So it is MB times M naught. We integrate from 0 to 4. Okay, from 0 to 4, and another one for cutting section number 2 will be equal to 0. So we get delta B naught as negative 5333.333 divided by EI. We can remain the answer in terms of EI because EI will be cancelled when we solve compatibility equation. So remain delta 1 naught or delta B naught in terms of EI, and then we continue to calculate FBB. FBB is MB square. If we use F11, it is M1 square. Okay, so for FBB we get 170.67. It is 170.67. This is the answer, 170.67. So after that, after we have determined displacement in primary beam, displacement in redundant beam, we have two systems. That's why two systems. For one redundant, we have two systems. We have two displacement. Two redundant, we have three system, we have 6 displacement. Okay, that's the difference. Okay, again, one redundant, we have two system, we have 2 displacement. Two redundant, we have 3 system, we have 6 displacement. Okay, this is for one redundant. So we substitute into the compatibility equation. And the compatibility equation, as I mentioned, we can choose either we want to label as B or as 1. So if we use B means B naught delta B naught plus FBB times BY, means that the moment equation for redundant also we use MB. If you want to use the other option, we can use delta 1 naught plus F11 times BY, means that the moment equation in redundant system is called as M1. So M naught for primary, M1 for redundant 1. So we substitute into the formula. So what we get is this. So this is compatibility equation. So always remember, when we write compatibility equation, we have to put EI. We have to put EI in the equation. We cannot simply cancel EI because displacement, when we divide the 5333.333 divided by EI, we get displacement value. It is 0.0 something. So remain EI in compatibility equation means you have to give the compatibility equation in EI form. And whenever we move to the next step, solve the redundant. When we solve redundant, we will cancel EI. We will cancel EI and we will get BY. Okay, we rearrange the equation and we will get BY is equal to 31.25. 31.25. So after we have determined redundant, we can continue to calculate remaining reaction, 3 remaining reaction using equilibrium equation. So or actually we can also calculate using principle of superposition as well. Either one can be used. Okay, so this example I have chosen equilibrium equation to solve for the remaining reaction. So what I actually did in this example is I put the redundant, okay, at position B. That is the BY value, 31.25. Then I can calculate remaining. AY, AX, and MA, just like we analyze a determinate beam. Okay, so we get MA equivalent to 150 and AY is equivalent to 68.75. AX will be 0 because this is beam. So using this, we can actually continue to draw shear force diagram and bending moment diagram. Shear force diagram and bending moment diagram. Since this is a simple beam, so by looking at the shear value, we can draw shear force diagram. Always remember that the diagram must be start at 0 position and end at 0 position. And the area of shear force diagram is equivalent to bending moment value. So this shear force diagram and bending moment diagram. Okay. So now we move to beam example 2. Okay, beam example 2. Okay, the same one, the same one, but this time I choose MA as redundant. I choose MA as redundant. I change also the P value and the length value. Even though I still use the same beam. Okay, this is the beam. Degree of indeterminacy is equivalent to 1. Degree of indeterminacy is equivalent to 1. So now I want to choose moment at A as redundant. So one redundant, we have two possible primary beam. For one redundant. Okay, one redundant, we have two possible primary beam for one redundant. One redundant, we have two possible primary beam. Two possible primary beam. Okay, because we know that for beam, we have two type of determinate beam. We have either cantilever beam or simply supported beam. So when we remove BY, we have cantilever beam. When we remove moment at A, we will get simply supported beam. So this is the case where I choose to have simply supported beam as primary beam. So I remove MA. So our redundant in this case is MA. So when I remove moment at A as the redundant, so I will get this equation. Okay, I will get this equation theta because the moment, okay, moment induced rotation. So we cannot use delta in this case. It is theta. It is rotation. It is theta 1 naught plus F11. F11 times MA is equal to 0. We can also write the compatibility equation in A label. It is delta. It is theta A naught plus FAA. AA times MA is equivalent to 0. But we must consistent. So if we choose to label as 1, so we have to use all 1. M moment equation in redundant system, we use M1. If we use equation number 1. Okay. So we have primary beam and redundant MA applied. So primary beam and redundant MA applied is the two determinate system that we need to analyze. So it is just simply supported beam subjected to different type of loading. So for primary beam, it is subjected to point load 125 kilonewton at the center of the beam. So due to that, we get AY and BY equals to 62.5 because it is subjected at the center, and this is simply supported beam. AX is equal to 0. So in redundant system, redundant MA applied, we have to apply a unit moment at A. We have to apply a unit moment at A, and due to that, we have to calculate AY and BY. So we get 0.1 negative 0.1 as AY and positive 0.1 as BY. Okay, and then since we have point load means we have to label C at the point load because the equation, okay, will be different before point load and after point load. That is why we have to have two cutting section. AC and BC, and we have to remain the two cutting section in the redundant beam as well. Okay, so we write the moment equation. So we have two cutting section. First cutting section is AC. AC origin A, the limit is 0 to 5. Okay, always remember that the moment direction, the moment is anti-clockwise, is counter-clockwise whenever origin come from left. Origin come from left, so that is why we get this. Okay, that is why we get this. Okay, and we continue to cutting section number 2. Cutting section number 2 is BC origin B. Okay, it is from 0 to 5, 0 to 5, 0 to 5. So the moment equation is clockwise whenever the origin come from right. Okay, then this the equation I tabulate into the table. The table consists of members, rows for members, origin and limit. Okay, and then M0 and M1. M0 and M1. M0 always for primary system, M1 for redundant number 1. Okay, so due to this, we calculate theta 1 naught, and F11 and F11. So we get theta 1 naught equal to 546.875 divided by EI, and 5 8 of F11 is equal to 5 over EI. So these two displacement we substitute into the compatibility equation. Okay, this is the compatibility equation that we refer. It is theta 1 naught plus F11 times MA is equal to 0. Okay, so we get MA is equal to 109.375. 109.375. Okay, in this case, in this example, I choose to calculate remaining reaction using principle of superposition. Principle of superposition means we refer back to the equation, general equation. It is actual beam equal to primary beam plus redundant applied. So we want to calculate AY in actual beam and AY in actual beam. We have AY in primary beam. We have AY in redundant beam. So this is all AY. Okay, one is in primary structure, one is from redundant structure. Okay, times with redundant. In this case, redundant is MA. That's why we have to times with MA. We times with MA. We just substitute the value and then we get AY equivalent to 73.4375 kilonewton and BY is equal to 51.5625 kilonewton. And lastly, we can transfer all the reaction, redundant and reaction, remaining reaction, 3 remaining reaction into the diagram, and we can continue to draw the shear force diagram and bending moment diagram. Okay, so this is whenever we remove moment at A as redundant. Moment at A as redundant. Okay, let's look at the next example. Okay, in this example, I want to focus on the effect of support settlement. The effect of support settlement, okay, take note that the settlement affect actual beam, affect actual structure. Remember, when we write compatibility equation, original equation, it is come from delta. Okay, let's say delta B, because redundant at B. Redundant is BY. Redundant is BY, means position of redundant is located at position B. So this delta B is equal to delta B naught plus FBB times BY. So where is actual beam? Actual beam is delta B. Actual beam is delta B. Normally, whenever when we don't have support settlement effect, delta, there is no value for delta. Delta B, that is why we write equation equal to 0. Delta B naught plus FBB times BY equal to 0. But now, due to support settlement, delta B is not equal to 0. It will be equal to the settlement given. It will be equal to the settlement given. Let's say settlement given is 30 mm. Settlement is given as 30 mm. 30 mm. So when settlement occur at B, the best choice is to choose redundant at B. Okay, means that the easiest way is by choosing redundant at the displacement position. Choose redundant at displacement position means that if settlement is located at B, the best choice is to choose redundant at the same position. Means we choose BY as redundant. Choose BY as redundant, so we write the compatibility equation as usual. It is delta 1 naught plus F11 times BY, but this time this is equal to negative 0.03. Negative 0.03. This negative 0.03 represent delta B naught, delta B or delta 1. Okay, it is the same. Because in compatibility equation, we use label 1 naught, 1, 1, so this is delta 1. If we use delta B naught, FBB, we use delta B. So this is the new the equation. That means when we have support settlement, it will only affect the displacement in actual beam. Okay, so it does not affect displacement in primary beam and displacement in redundant beam. That means we just need to change the value, the delta B value. Okay, before this it will equal to 0 whenever there is no settlement effect, and when settlement is given in the question, we need to consider that, and we just need to change delta 1 from 0 to negative 0.03. Negative 0.03. Okay, so as usual, we go step by step. We have to calculate delta 1 naught and F11. F11 using this formula. So again, we have to have the primary beam and redundant BY applied as redundant beam. Okay, we have two cutting section. So we calculate reaction, and then we calculate reaction, and then using that we will write moment equation, and moment equation we substitute into this displacement formula. They are delta 1 and F11, so we get displacement in terms of EI. And whenever we want to solve this compatibility equation, we have to have EI value. Unless the displacement is given in terms of EI, then only we don't have to have EI value. Okay, so if settlement is given in mm, in meter, so we have to have E and I value so that we can solve the compatibility equation. Okay, let's say E and I is given like this. Okay, so what we need to do is we have to substitute into the compatibility equation. And we get, okay, 36,000 divided by 10,000. Okay, then we get like this. So finally, we get redundant equal to 61.98. So we can check when we don't consider support settlement, the value of redundant will be different. Okay, it will affect the reaction whenever settlement is given. We can see the trend whether the value, the reaction at B increase or decrease. Okay, we can try to change with another settlement to check the effect of settlement whenever we solve for the redundant value. Okay, so finally we solve the remaining. And then we draw the shear force diagram and the bending moment diagram. Okay, so this is the same beam. I just change the loading, the length, and I put the displacement, the support settlement, and then this is how we analyze. Support settlement. Okay, in beam 1 redundant. Okay, move to beam example 4. I'm not sure whether I have done this until the end. Yeah, this is full example as well. Okay, but this time this beam has two redundant. Okay, remember I said just now, when we have two redundant, we have three systems. When we have two redundant, we have three systems. Two redundant means redundant 1, redundant 2, we have to plus with primary system. So we have three systems, three determinate system. We have primary beam, we have redundant 1, we have redundant 2. Okay, for the possible primary structure, we have three. Possible primary structure, we have three types. Possible primary structure. For the possible primary structure, we have three types. Okay, for the possible primary structure, because we have to remove two. So if we want to have cantilever beam, we have to remove BY and CY. So that is the first possibility. Okay, if we can also remove one moment from A, one redundant from A, that is moment, and remove CY. Okay, remove CY. So we get determinate beam, cantilever end at C. Okay, redundants are MA and CY. So this is also determinate structure. Okay, this is the second possibility. So always remember that when we have simply supported beam type, okay, the stable structure must have at least one pin and one roller. Okay, for the third possibility, we remove one from A and we remove BY. So we get simply supported beam. Okay, so for the general equation of compatibility equation, we get from principle of superposition. I have also derived this, okay, previously, and we finally get the equation in matrix form like this. So this will be the standard equation of compatibility equation when we have more than one redundant. For two redundant, for three redundant, we can apply this compatibility equation. Except for three redundant, we will have F11 until F33. Means that we will have 3 by 3 matrix for the flexibility coefficient. Okay, so this is the compatibility equation. The standard one. Okay, delta label not we use for primary system. So when we see this delta 1 node and delta 2 node, we know that this is the two displacement occur at primary beam. Delta 1 node and delta 2 node are the two displacement occur at the two redundant position, because we have two redundant, we have two position. Means that delta 1 node and delta 2 node are the two displacement which is located at position redundant number 1, position redundant number 2 in primary beam. And we combine all displacement into redundant beam in matrix form. It is 2 by 2 matrix because of two redundant. If we have three redundant, we will have 3 by 3 matrix. So this matrix have this matrix actually is the real matrix. So we have to apply the metric characteristic, which is symmetry. That is why we have F11, F12, and the value is equal. Okay, we have F11, F12, F21, F22. This is 4 by 4, 2 by 2 matrix. These four values is called as flexibility matrix. Okay, so the first redundant is BY. The second redundant is CY. Means that we have to refer to line as well. So it means that this is line number 1, line number 2. So label the first label 1 here, 1 here, 1 here, redundant 1. So all referring to the position. Of redundant number 1. And for line number 2 is for position redundant number 2. So the notation that we use, 2 here, it is 2, 2, CY is redundant number 2. Okay, CY is redundant number 2 because the first notation we actually refer to the position. The second notation refers to the type of beam, type of structure. Okay, I delete back this. Okay, when there is no support settlement effect, as usual, it will be equal to 0. Means that delta B is equal to 0, delta C is equal to 0, delta 1 and delta 2 equivalent to 0. So there are 6 displacement in this equation, 6 displacement, 2 displacement, 2 redundant, 3 system, 6 displacement. 2 redundant, 3 system, 6 displacement. 6 displacement. So we have 6 displacement. 6 displacement. You don't have to remember any formula because when you label the displacement correctly, just use the notation to know which system we have to times with system. Okay, which system. Okay, for example, so we have label 1 knot, we have label 2 knot, we have label 1 1, we have label 1 2, we have label 2 1, we have label 2 2. So for the moment equation that we need to integrate, we have to integrate 2 moment equation. We just need to refer to the notation 1 and knot. Okay, same to this. And then we have 2 knot, 2 knot, 2 and knot, M2, M knot. And then F11, M1 square, M1, 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 M2. For F12, M21, 2, 1, and then 2, 2, we get M2, M2. Okay, so we will have three system. We have 3 systems start with M naught for primary system, M1 for redundant 1, M2 for redundant 2. 3 system, 0, 1, 2. We just need to follow the flow. Okay? And actually the equation you don't need to write as well. Whenever you solve the example, the question, okay, the beam, the structure, okay, you don't need to write the formula because we know which system times which system, okay, by looking at the notation that we use, Okay, so we have 3 systems. The first system is primary beam. So in primary beam, so I put wrong label here. This is M naught actually. This is M naught. Okay, this is M naught. Okay, we have primary beam, we have redundant 1, we have redundant 2. Primary beam, we have redundant 1, we have redundant 2. Okay, 3 system, primary beam, redundant 1, redundant 2. And for all these 3 systems, it is actually all determinate system, determinate beam. So we just have to calculate reaction and write moment equation as usual. Okay, so the system, where is the diagram? Okay, so this is the primary beam. The primary beam is okay, this beam, the UDL is 60, so we get 240 for the reaction for the AY value, and we get moment is 1920. It is negative, so we have 2 cutting section. Okay, AB as the first cutting section, BC as second cutting section. So we have 2 cutting section. Okay, for cutting section number 1, moment is counterclockwise because origin come from left. And for cutting section number 2, moment is clockwise because origin start from right. So we write the moment equation and we get the moment equation like this. Okay, so this is the moment equation for section number 1, origin A, section number 2, origin C. Okay. So when we move to redundant applied, redundant BY applied is actually redundant number 1. Redundant number 1. So again, this is for M1. We have to calculate reaction and write the moment equation. Where is the diagram? So this is the diagram. Okay, this is the diagram. Okay, this is a unit value of BY at position B. A unit value. A unit value. So we have two sections. We have two sections. We have two sections. For section number 1, section number 1, this is M1. This is M1. So this is M1. So we get the moment equation. It is 6 minus X because X is located here. This is X. Okay, so we write the moment equation. And for cutting section number 2, moment is equivalent to 0 because of this. Moment is equal to 0. And okay, so okay, so this is the equation. It is 6 minus X, 6 minus X, and 6 minus X, and M is equal to 0. M1 for section number 1 is 6 minus X, by referring to the diagram previously. Okay, and M1 for section number 2 is equivalent to 0 because of the cantilever N. Okay, so the last section, the last system is redundant CY applied. Redundant CY applied is the redundant CY applied. Okay, is for M2 because redundant number 2 is CY. Okay, redundant number 2 is CY. So again, we have to write the equation, the two moment equation which come from two cutting section. So we get 12 minus X and for section number 1 and X for section number 2. So we transfer all the moment equation in the table. We transfer all the moment equation in the table. So in the table we have the column for member origin limit. Member origin limit because origin is very important. Limit, okay, is limit is also important because we will substitute the limit in whenever we want to calculate displacement. Okay, so we have we have 3 columns for the moment equation. Start from M0 followed by M1, M2. So we just have to follow the flow. Okay, follow the flow. So this is 1, go to this is 0, 0, go to 1, go to 2. Okay, so 0 or not is always symbol for the primary system. So 1 is for redundant 1 and 2 is for redundant 2. So we transfer all the moment equation into the table, into this table, and we determine all the displacement, all 6 displacement. We determine all 6 displacement. Okay. And remember, F11 and F12 is the same, so we just need to calculate once. Okay, so these are all the displacement in terms of EI, and we don't have to substitute EI unless we have to consider displacement, and displacement is given in unit meter or mm. Okay, these are all the 6 displacements. So what need to do next? What we need to do next is we have to substitute into the compatibility equation. We have to substitute into the compatibility equation. In terms of EI, remember the compatibility equation must be given in terms of EI. Okay, in terms of EI. And then whenever we solve this equation, we just need to solve using calculator directly. You don't need to write it back into 2 simultaneous equation and do it manual calculation. No need to do that. Okay, so BY and CY by using calculator equals to 152.92 and 82.83, okay, for CY. Okay, then by using principle of superposition, you have 2 choices. Either you want to solve by using equilibrium equation. Equilibrium equation means you have to just substitute back the value 152.92 here, 82.83 here. So this is UDL 60 previously. So then you have to calculate using equilibrium equation if you want. And we have another choices to calculate the remaining reaction by using principle of superposition. Principle of superposition. This is MA in primary system. Okay, 6 is MA in redundant number 1. 12 is moment equation, moment at A in redundant number 2. Okay, and for redundant, we have to times back with redundant. Redundant number 1 times BY, redundant number 2 times CY. So this is how we apply the principle of superposition in order to calculate remaining reaction. So we get this value and this value, and AX, because it is beam, it is equivalent to 0. So, okay, the same example. I extend this question. I put here the settlement. So whenever the question, okay, normally the question have more than one sub question. That is not one question only. Basically, question A, question B, question C, right? So basically, question A may be asking you to solve without any effect, and then when move to question B, you need to consider support settlement, for example. So for example, after you have calculated all the reaction like previous, okay, answer, okay, this one. Okay, continue to consider settlement at position B. Remember, whenever settlement is located at position B, whenever redundant is also at the same position, so it is very easy for us to apply. Okay, so we have to apply delta B, which is because R1 is BY. R2 is CY, so we have to apply delta 1, which is equal to negative 0.03. So it will not affect any displacement value that we have just calculated. We just need to change, okay, in actual system. Means that previously the displacement in actual beam at position B is equal to 0. Now it is equal to 0.03, negative 0.03. So by substituting this, okay, negative 0.03, okay, what we need to do again, whenever we have to consider support settlement, we have to have E and I. We have to have E and I unless settlement is given in EI, in terms of EI. Okay, so we put this into the compatibility equation. Okay, we get the new compatibility equation, and then when we solve, we get this value. Okay, normally whenever settlement is given in the question, we will get different answer. Means that displacement will always affect the reaction. The settlement given in actual system, we always affect. Then if we have question like this, one without settlement and another one with settlement, we can compare the result, and we can see which one get lesser value, okay, which one got higher value. Okay, then we can continue to calculate remaining reaction. So the same step, we just need to change the redundant value. Just need to change redundant. So we just need to change redundant here. So the rest are all same. Okay, then we will get the new reaction after considering support settlement at position B. actually, whenever the redundant and settlement is located not at the same position, we can still calculate, analyze the redundant value and variation, but we have to do some modification in the compatibility equation. Okay, next. Okay, so this is one blank example, one blank question. Okay, so we take this time to analyze this together. So this is beam, indeterminate beam. This is indeterminate beam. So P is 15 kilonewton. We have W2, the triangular load is W2. The triangular load is 10.2 kilonewton per meter, and we have W1 UDL equal to 8.8 kilonewton per meter. So I now want to label, label this as A, B, C, and D. Okay, so we have 1, 2, 3, 4 join. We have 4 join. And we will have we have how many cutting section? We have 3 cutting section. So in this case, we have 3 cutting section. Okay, we have 3 cutting section. And this beam has two redundant because B is roller, C is roller. B is roller, C is roller, A is cantilever, and D is fixed. So we are going to do this together. We will analyze this beam using flexibility method. So in this case, we have 2 degree of two redundant because degree of indeterminacy is equal to 2. Okay. So this is indeterminate beam. To the second degree of indeterminacy. We have DOI. DOI is equal to 5 minus 3 equal to 2. 5 minus 3 is equal to 2. So we can choose now the redundant. Okay, let's say we choose. Okay, let's say we choose R1 and R2. R1 equal to CY. R1 equal to CY. CY. And another one is okay, we have R2. We have to remove another one. I want to remove moment at D as the second redundant. Okay, the second redundant, this is redundant number 2. Redundant number 2 equal to moment at D. So it is moment at position D. Moment at position D. So having this actually, after we have chosen redundant, we have to be able to have the standard form of compatibility equation. The standard form of compatibility equation. Okay, the standard form of compatibility equation. Okay, standard form of compatibility equation. So this is A, this is B, this is C, this is D. Okay, the compatibility equation, the standard form of compatibility equation equals to okay, it will be two value. Two redundant mean two a matrix. The matrix is two, like this one. Okay, so the first redundant is CY. So CY is PP induced deflection. So it is delta. It is delta 1 node. It is delta 1 node. So this is 1 node. And redundant number 2 is MD. Redundant number 2 is MD. So it is theta. It is theta because it is moment. So where is theta? This is theta. Moment induced rotation. Moment induced rotation. It is delta 2 knot. Delta theta 2 knot. Okay, we have to plus. Okay, we have to plus. Remember, we have two redundant. We have two redundant. We have 2 by 2 matrix for flexibility matrix. So all the small letter of F represent flexibility matrix. Represent flexibility matrix. Okay, so we have 2 by 2 matrix. 2 by 2 matrix. Standard form of matrix. Standard position of matrix. So this is F. This is also F. This is also F. This is also F. This F is actually for the flexibility coefficient. Flexibility coefficient. So for the matrix, this is position 1, 1. Standard form of matrix. This is position of 1, 2. This is 2, 1 position in the matrix. And this is 2, 2 position in the matrix. So this will, okay, we need to times with, okay, we need to time with redundant. Redundant number 1 is CY. Redundant number 2 is, okay, redundant number 1 is C, Y. Redundant number 2 is M, D. Okay, and this is equal to when there is no effect of settlement. When there is no effect of settlement, so it is just equal to 0. It is just equal to 0. So this is 0, 0. When there is a settlement given in the question, we need to consider settlement, then only value for this will be changed. Okay, so by having this compatibility equation, okay, having this compatibility equation, we know that there are 6 displacement, 2 displacement from each system. 2 displacement from primary system, 2 displacement from redundant number 1, 2 displacement from redundant number 2. Totals are 6 displacement. Okay, we have 3 system, primary system, and redundant number 1, redundant number 2. Okay, so we have 3 systems. Start with the first system. It is primary beam. Okay, it is primary beam. And in primary beam, what we do, we calculate reaction, and we write moment equation. Moment equation is, here is M naught. Moment equation is M naught. Naught is always labeled for the primary structure. label for the primary structure. Okay, so this is for the first system, primary beam. Primary beam. Okay, let's calculate the reaction for this beam. Calculate the reaction for this beam. Okay, so please calculate reaction. Calculate reaction for this beam. Okay, for the primary beam, what we have is P is equal to 15. W2 is equal to 10.2. W1 is 8.8. It is 2 meter, 6 meter, and 8 meter. Okay. So D is now pin. So dy dx, and cy just now is cy, right? So by. So here is by. So this is triangular load. Okay, this is dx dy because of the pin support. Okay, so we calculate moment, apply moment to calculate reaction at B and reaction at D. Okay, reaction at B and reaction at D. Take moment at D is equal to 0. Okay, so it is negative 15 times 16. 15, it is 15 times 16. Okay, triangular load, the area. Triangular load, load, the area is 0.5 times 2 times 10.2. Okay, the distance is The distance is 2 over 3. 2 over 3 times 2. It is, okay, it is 2 over 3. 2 over 3 times 2. It is 1.333 plus 14. Plus 14. The distance. So it is 15.333. 15.333. Okay, and then UDL. UDL is, okay, UDL is minus as well, minus 8.8 times 14 times 14 divided by 2, 7. Okay, it's also minus, plus BY plus BY equal to, BY kali dengan 14 equal to 0. Okay, so please calculate what is the BY value. BY value. It is negative 15 times 16. All minus, right? So 0.5, this one is minus. So minus by 0.5 times 2 times 10.2 times 15.333. We minus by 8.8 times 14 times 7. Divide by 14. So we get BY. BY is equal to negative 89.914 kilonewton. BY. Okay, BY. So total Fy equal to 0. So what we get is negative 15 minus area 0.5, 2, and 10.2 minus 8.8 times 14. Okay. BY is positive. BY is positive. Okay, BY plus BY is 89.914. 89.914 plus dy. So we get dy equal to negative 15 minus 0.5 times 2 times 10.2 minus 8.8 times 14 plus 89.914. So we get dy equal to 58.486 kilonewton. Okay, so it is 58.486 plus 89.914 minus by 15. We minus by 88.8 times 14. We minus by 0.5 times 2 times 10.2. It is 0. Okay, so this is reaction in primary. Reaction in primary beam. Reaction in primary beam, we get By is 89.914 and dy equal to 58.486. Okay, now we move to moment equation. So we have how many cutting section? We have 3 cutting section. We have 3 cutting section. We have 3 cutting section because we have C here. Okay, so we have to have 3 cutting section. So we have cutting section for AB, for BC, and for CD. 3 cutting section. We have to have 3 cutting section. So okay, I label as numbering. I label as number here. So the first cutting section is AB. This is first one. The second cutting section is BC. So this will be the first. This will be the second. This will be the third cutting section. Okay, so for cutting section number 1, we choose A as origin. Cutting section number 1, we choose A as origin. So limit will be 0 to 2. Okay, and okay, I like to type the details. Okay, so we have section number 1. For section number 1, we have section 1. For section number 1, origin is A. It is AB. AB origin. Origin A. Origin A. So AB origin A from 0 to 2. From 0 to 2 meter. From 0 to 2 meter. So we draw the section. Okay, what about the section? So the section is like this. Okay, it is the moment it is 15. So this is 15. This is 15. And don't forget to find the new W value at the cutting section. At the cutting section, we have to calculate what is the value. If this is 10.2 for 2 meter, so we have to have, okay, if this is X, so we have to interpolate to get the new value at this position. Okay, this one we have to use the trigonometry. So if okay, it is the new value here to new W. So it is 10.2 divided by 2 is W divided by X. So W is equal to 10.2. It is 5.1x. It is 5.1x. 5.1x. So this is 5.1x. Okay, the W. This is M naught. M naught. Okay, X is from A. This is X located at A. So we have to write the moment equation by taking the moment at the cutting position. So we write the moment equation. This is negative M naught. Negative M naught minus 15 times X. 15 times X. We minus again. Okay, the area of the triangular, the area is 0.5 x, 5.1 x. Okay, and it is 2/3 times x as well. So this is equal to 0. This is equal to 0. So negative M naught, it is minus 15 times x. Minus 15 times x, we minus the area of rectangular is 0.5 times x times 5.1x, and then the centroid is 2/3 times x. Okay, so we will get M naught for section number 1. M naught for section number 1. So we get M naught. Equal to, this is negative 15x. Negative 15x, so we get 0.5 times 5.1 times 2 divided by 3. So it is x cubed, 1.7. 1.7 x cubed. Okay, x cubed. Okay, this is for section number 1. Section number 1. Okay, so we continue to section number 2. For section number 2, okay, it is section. Which is BC. Okay, choose the best origin. Choose the best origin. Choose the best origin. Okay, the best origin. Okay, means that not taking from A and A, because we want to. We don't want to analyze the triangular load anymore. Okay, so I want to choose origin at D. Origin at D. D is the origin. Origin at D. Origin at D. So when D is origin, limit will be from 8 to 14. from 8 to 14, origin at D. 8 to 14. From 8 to 14 meter, the limit of X. Okay, section number 2. Section number 2, BC, origin at D. Okay, origin at D. So what we have is, okay, what we have is this. Okay, reaction is 58.486. 58.486. It is UDL. So this is D, this is C. Okay, this is cutting point, moment M naught. Moment M naught. Okay, this one is 8.8. 8.8. So origin start from D. Origin start from D. So the length, okay, total length here is X. Okay, and we have C to D. C to D equals to 8. C to D equals to 8. This is 8. This is X minus 8. Okay, and actually we can also choose C as origin. Okay, we can also choose C as origin. We have option. We can choose any origin that we like. Okay, let's say we try to write the moment equation and then we try to compare. If we choose C as origin, which one will be easier? Which one will be easier? Okay, because we remove CY. Okay. Okay, so we write the moment equation by taking moment at the cutting position, cutting point. Okay, somewhere between B and C. Somewhere between B and C. So the moment equation is M naught. This is M naught. It is minus 58.486 times X. Okay, and we get 8.8 is positive. It is 8.8 times X. 8.8 times X for the area, and for the distance it is X divided by 2. Okay, simple, because there is no load on at point C. So it is just like this. It is 8.8, so we don't need to have this. Okay, so it is 8.8 times X for P, and for length it is X divided by 2. So this is equal to 0. So we get M naught equal to 58.486 X minus 4.4 x squared. 4.4 x squared. Okay, so the next section is cutting section number, for the cutting section number 3. Okay, for the cutting section number 3, section number 3 is CD. Number 3 is CD. CD origin. Origin D as well. And X is between 0 to 8 meter. Okay, previously is 8 to 14 because it is for BC. Now it is from 0 to 8 because it is for CD. And actually we do have the same equation. We do have the same equation because we have the same section, the same diagram. So we get this M. Okay, M naught for this is equal to 58.486 x minus 4.4 x squared. Okay, this will be the equation. Okay, now we have all the moment equation for primary beam, which is M naught for 3 cutting section. Okay, we now move to the second system. It is redundant. It is redundant CY applied. It is redundant CY applied. So we move to redundant CY applied. Redundant, it is redundant CY applied. CY is assumed as an applied load. Okay, as an applied load, this is redundant CY applied. Okay. We have to calculate reactions and moment equation. And moments equation. And moment equations. So this is M1. This is M1. This is M1. Because CY is redundant number 1. CY is redundant number 1. Okay. So Okay, we have to apply a unit value of CY. So I remove everything here. It is the same type of beam, but this time it is subjected to a unit value of redundant. A unit value of redundant. So it is located at C. It is located at C. So here is a unit value. A unit value of CY. A unit value of CY. So we have to calculate the reaction at BY and D, at B and D. Okay, so taking moment at D, we have to take moment at D is equal to 0. So it is BY 14 plus 1 times 8. So this is equal to 0. So we get BY is equal to 8 divided by 14, negative. 8 divided by 14, we get 0.571. 571. So if BY is equal to negative, negative 0.571, so we get dy is equal to 0.429. This is also negative. Okay, so dy is negative 0.429. Py is negative 0.571. So we have 3 cutting section. Section 1, section 2, section 3. Okay, section 1, section 2, section 3. Okay. And then okay, we calculate reaction for system number 3. System number 3 is redundant M. Redundant M. MD applied. So this is M2. So we get okay, we have to apply moment at D. Moment at D is equal to 1 and we have to calculate By and Dy. Okay, it is By times 14. By times 14 plus 1. Okay, this is equal to 0. So By is equal to 1 divided by 14. 1 divided by 14, negative. It is negative 0.0 0.714. So dy is equal to positive 0.0714. So dy is 0.0714 and by is negative 0.0714. Okay, so all this we have to write moment equation, and I will straight away write the moment equation in the table. In the table, so we have 3 cutting section. Okay, we have 6 row. Okay, so we have member. Member origin dulu. Origin. Limit. Limit. We have M0, M1, M2. M0, M1, and M2. So all moment, this is M, 0, 1, 2. Okay, we have member. We have member AB. We have member BC. We have member CD. Okay, origin previously we choose A, and then D and D. Okay, for the limit, we choose from 0 to 2, and then we choose 8 to 14, 8 to 14, and we choose 0 to 8. And for M0, okay, for M0, we get negative 15x minus 1.7 x cubed negative 15x. It is negative 15x minus 1.7 x cubed. X cubed. This is x. 58.486. 58.486 x minus 4.4 x square. Okay, so for for redundant CY applied, M1 for AB it is equal to 0. This is 0. For redundant MD applied, again A for AB it is equal to 0. To 0. And for it is, this is 0.429. This is M. So it is 0.429x negative 0.429x negative 0.429x. Okay, and for another one, we get this 0.429. This is 1. This is 8. This is x minus 8. So this is M. So M minus 1 and minus 1 times x minus 8. Okay, it is plus with 0.429x equal 0. So it is M minus x plus 8 plus 0.429x. M minus x plus 8. So it is M equal to negative 8. Negative 8. So it is negative 1 negative. It is 0.429. So we get 0.571x. Okay, so it is 0.571x minus 8. So that is the second equation, 0.571. Five seven 1 571 minus 8. Okay, and then for the redundant number 2, it is 0.0714 moment. This is 1. This is m. So it is m plus 1 minus 0.0714x equal to 0. So m is equal to 0.0714x minus 1. Okay. It is 0.0714. 0.0714 minus 1. Okay. Okay, so this is the moment equation from 3 systems: primary system, redundant 1, and redundant number 2. So from this, we will continue to calculate. Displacement, 6 displacement. Okay, to calculate 6 displacement, so it is delta. It is delta 1 naught, 1 naught. Okay, it is 1 over EI. 1 over EI. 1 over EI. We integrate from, okay, for AB will be 0 because M1 for AB is 0. So move to BC. BC is from 8 to 14. 8 to 14. And the equation is, okay, I copy this. The equation, it is 1. This is 1. M1. It is M1 times M naught. M naught dx. Okay, dx. We have to plus with, okay, for CD, it is 1 over EI. Okay, we integrate from 0 to 8. From 0 to 8. Okay, it is M1. Negative 0.429. dx. Okay, so now we will calculate this value. We have to calculate the delta 1 node in terms of EI. Okay, so let's calculate the value. (0.571x minus 858.486 x minus 4.4 x square. (58.486) from 8 to 14. It is negative 1401.944. Okay, another one is negative 0.429 x times with 58.486 minus 4.4 square from 0 to 8. So we get negative 2349.209. 2349.209. So this one equals to 1401.944 negative 3751.153. 3751.153. 153. 153. This is equal to EI per EI. So this is delta 1 not delta 1. Okay, so we move to theta 2 not. Okay, we move to, okay, it is theta 2 not 2 not to 1 over EI. We integrate moment equation. Okay, again, it is from 8 to 14. Means that we actually don't need to analyze M naught for section number 1. Okay, so the equation is M2 times M naught. M2. M2 is, okay, I copy this. And M naught is this. X. And then for CD, if EI is not constant, we have to consider it here, right here. Okay, in this case, we consider EI are all constant. 1 over EI. So from 0 to 8. It is M2 times M naught. This is M2. To M naught. And M naught is close bracket dx. Dx. So this will be equal to Okay, now we will calculate the value for displacement delta theta 2 naught. Theta 2 naught. Okay, so we calculate this delta 2 naught and continue to calculate F11 until F22. If 175.09099. And the second one is 0.00714 minus 1, 58.486 minus 4.4, 0 to 8. Fifty-eight point four eight six for x minus 4.4 x square from 0 to 8. We minus by 729.631. So 175.099, we get negative. We get negative 904.731. 0.731. 731. So we just need to continue to calculate F11, F12, F21, and F22, okay, to get all 6 displacement, and then we need to substitute into the compatibility equation to solve for the redundant. Okay, so this one we have to continue. Of course, we have to continue to calculate F11, and then F. Okay, wait. Okay, so this is actually how we analyze beam to redundant. Okay, where the most complicated part is when we analyze moment equation and then the displacement, because once displacement has been determined, then the rest is all substituting the value into the equation, and then we can solve using equation. So what we need to do after this is we have to continue to calculate. F11. We have continued to calculate F11. Okay, let's continue. Okay, let's continue. Okay, insert equation. It is F11. F11. Actually, you don't need to give or rewrite again the equation. You just need to give the answer only. No need, if you don't want to write equation again, also okay. Don't need to wasting time rewrite equation that you have actually write in the table. Okay, so I just write like this because I want to show to you this is the process actually that we do whenever we analyze the displacement. So the moment equation we get from table and we integrate to get the displacement. We have 6 displacement, delta 1 node, delta 1 node, and then theta 2 node, and we have another 4 displacement which come from redundant system. Okay, we continue to calculate F11. So for F11, we, okay, again, we integrate. So it is in terms of EI. Okay, it is in terms of EI. So by looking at the table, I will calculate the value directly. It is M1 square. Now, it is M1 square. So I integrate 0.571 alpha x minus 8 square. It is from 8 to 14. From 8 to 14. So it is 23.599. 599. Okay, for BC, and for CD. For CD, it is negative 0.429. Okay, x square from 0 to 8. So we get 31.41. 31, it is positive. 31.41. 31.41, so we plus with back with 23.599, so we get 55.009. So what we get is not this one. Okay, so it is in terms of EI, it is 55.009. So this is F11. So we continue to calculate F12 and F22. Okay. Now we want to calculate F12, which is equivalent to F22. Which is equivalent to F21. F21. For F for the flexibility matrix. So this is F21. Okay, now we will calculate. We will calculate M1 times M2. M1 times M2, it is 0.571x minus 8 times with 0.0714 x minus 1, limit from 8 to 14. From 8 to 14, we get 2.947. Okay, this is 2.947. 2.947. 2.947, and another one is negative 0.429 x times with 0.0714 x minus 1 from 0 to 8. So this is equal to 8.5. 8.5. So plus back with 2.947. So we get 11.447. 11.447. 11.447. So last one is F22. Last one is F22. So last one is F22. F22. And F22 equals to 0.0714 minus 1 square from 8 to 14. From 8 to 14, it is 0.368. 0.368, and then 0.0714 x minus 1 square. It is from 0 to 8. This is 4.3. This is 4.3. 4.3. So we plus with 0.368. So we get 4.668. It is 4.668. Okay, so these are all the 6 displacement. So now we want to substitute this into now we want to substitute this into compatibility equation. So we substitute all displacement into the compatibility equation. It is 1 over EI. This one is 1 over EI. 1 over EI. Okay, the first value is negative, this one. Okay, the first value. The second value is okay, plus okay, we have 55.009. We have 11.447. 11.447. And then we have 4.668. 4.668. And this equals to 0 when there is no effect of settlement. Then, sorry, I forget to put redundant here. If it's redundant, CY and MA. Y MD, not MA, MD. Okay, so this is the compatibility equation. So what we need to do now is we have to calculate CY and MD Calculate CY and MD using calculator. Okay, using calculator. So use equation to unknown, it is 55.009, 11.447, 3751.153, 11.447, 4.668, and 904.731. So we get CY equal to 56.89 and first. Okay, CY equals to 56.891 kilonewton. Okay, and MD equals to 54.306. This one is kilonewton meter moment. Okay, so after this, we continue to calculate remaining reaction. Okay, continue to calculate remaining reaction, okay, using principle superposition. Okay, so A, what we want is BY. BY. So BY is equal to BY 89.914. 89.914. Okay, we plus with negative 0.571, negative 0.571. So what minus? Positive, negative, minus. Minus 0.571, 0.571, 0.571. The first redundant is, this is 571, 571. The first redundant is CY. The first redundant is CY. This is C, this is Y. Okay, and then BY for this one is negative 0.0714, minus also minus 0.0714. Okay, this is BY in redundant number 2 times with M times with MD. The redundant that we remove. The redundant that we remove, we have to put back whenever we want to calculate the remaining reaction using equilibrium, using principle of superposition. Okay, using this we will get BY in actual system. Okay, it is 89.914. We minus by 0.571 times with 56.891. Okay, we minus by 0.0714 times with 54.306. It is equal to 53.2552 kilonewton. Okay. And for dy, okay, for dy also same process. So it is dy. So dy in primary beam is 58.486. 58.486. 58.486. Okay, and then dy for redundant number 1 is negative 0.429. Negative 0.429. 429. Negative 0.429. 429 CY and 0.0714. dy is positive 0.0714. This is positive. Positive. Okay, one positive, one negative. Okay, so calculate dy value. It is 58.486 minus 0.429 times 56.891. Okay, we plus with 0.0714 times with 54.306. So we get 37.9, 37.957. 37957. 37.957. 957. Okay, and dx is equal to 0. Dx is equal to 0. So now we have already calculated all reactions in this beam. So we have all 5, but not A. dx is equivalent to 0. Okay, so to check back this whether it is right or wrong. Okay, the process is this is the process. You just have to follow the process whenever you want to analyze. Okay, analyze beam, analyze frame. The process will be the same. The formula will be the same. Okay, so after this, normally we will continue to. Normally the question, sometimes question asks you to draw diagram, sometimes not. Okay, if the question asking you to calculate redundant and then remaining reaction, this is how we analyze. Okay, and this question we can actually continue to draw. Okay, the diagram. So this is triangular load, this is UDL. Okay, this is 15, 10.2, 8.8. Okay, we have BY. BY here is 53.552. We got CY. CY equal to 56.891. And then we get DY. DY we get 37.957. And we get moment. Moment equal to 54.306. 54.306. Okay, the distance is 2 meter, 6 meter, and 8 meter. So what we need to do is we just need to check back whether the system is in equilibrium. Check with equilibrium equation. Check with equilibrium equation whether this is the right answer. If it is not right, we have to check back whether we have done mistake when we write moment equation or when we substitute the moment equation into the displacement formula. Okay. So let's say we calculate it is triangular. Triangular 0.5 times 2 times 10.2. Okay, we plus with 15. We plus with 8.8 times 14. 14. Okay, we minus by 53.552. We minus by 56.891. We minus by 39.9957. 39.957. Okay, we get negative 2. Okay, this is correct, but we assume this 2 value as ralat. Okay, so if you want to check for the because normally we will get plus minus 2 because of the decimal places that we take along the calculation. Okay, so we can also check for the moment. Okay, and if we draw diagram, we can see whether the answer is correct or not by looking at the diagram, because whenever the diagram close a closed loop, then the answer is right. Okay, so this is how we analyze. This is full analysis of flexibility method, analysis of indeterminate beam. So this normally flexibility method, the concept is simple, but the most complicated part is whenever the structure or the beam has combination of many loads. Okay, different type of loads like this. So you have to practice in writing the right moment equation about the cutting section. Make sure everything about that is okay. Then you should be you should be able to do the analysis. Okay, basically the problem of flexibility method is whenever student cannot analyze fraction and cannot write the moment equation. Okay, so this is how we analyze. Okay, so now it's 12:15 already. So in the next session, I will do one frame example, and one truss example. One frame example and one truss example. Okay, I will also send to you another type of beam problem, and you can do as your formative assessment, as preparation for test. Okay, I think the next session will be tomorrow, not today. Today evening will be tomorrow morning. Okay, so you are invited to join. So, and inshallah for next week, even though we don't have class because we have in faculty I have programs, and we are not only me, it is all lecturers, many of lecturers join the program. So I don't have I don't have time to do class, follow the timetable, so I replace with this session. And because your test is on next Friday, so inshallah if I have time, I will do something like this daily, maybe 1 hour or 2 hour after 5 o'clock. After 5 o'clock, about 5 to 7 daily. Okay, about 5 to 7 daily. We will continue to do many more examples. Okay, covering both flexibility method and moment distribution method. Okay, as preparation for your test. Okay, so there will be no class session for next week. So we will focus on another workshop, daily workshop, as preparation for your test. So thank you for joining. So for those, okay, please. tell your friend, for those who not join this session. So actually the link given can be used to watch at any time. So just use the link. Okay, so thank you very much. Thank you for joining. So inshallah we will meet again in the next session. So okay, wait for my announcement in the Microsoft Teams channel. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.